Hello. In this video, we'll be using the grassman numbers that we learned in the last video to show a cool application of the formalism of fermions in quantum field theory. So, we're going to calculate the path integral for fermions, and we're going to see something nice that happens. So, for the action, we want our action to be bosonic. So I'll say function phi1, phi2. So we want two fields, these two fermion fields give bosonic action, such as for bosons, we can remember that for free bosons, we have the derivative term plus this mass term. So similarly, well, actually, we could say this, where phi is the bosonic field, and then A is the operator. Linear operator, so to get the equation motions, and in this case, it's the Klein-Gordon equation for scalar, even bosonic quantum field theory. And then we can take the propagator, which is the Feynman propagator. So the probability that a particle will start off at y, a particle currently at y will end up at x. So we get the propagator from the path integral by taking the inverse of the operator gives you the equation of motions. So, so once we took the partition function, it was just a gamma function. We integrated over all the fields, and what we ended up with was just a gamma type function. X squared, and then the beginning was pi, and a determinant of A. So now we're going to turn back to the fermion case. Our path integral is e to the s of 1 phi 2 minus over h bar. And you see we can expand it. This is, integrate this, all the fields, we get the partition function. So we're summing all the possible states. And then what this gives us is 1 minus half phi 2. And then we could expand it, let's do another term, plus 1/4, and then factorial a squared phi1, phi1, phi2, phi2. We know it's equals 0, and all the terms after it will also equal 0. So we are left with just this, and the integral. We take the integral for this, gives us 0. Take the integral for this, gives 1. So now we're just left with A, the operator. And then, of course, when we have a lot of fields, we could make this into a matrix. We could express this in matrix form. And this used to be the determinant. Okay? So we see that in the fermion case, it is the opposite of the boson case, where we had the determinant, a factor of the determinant at the bottom. The propagator will be the same, won't be the inverse. Well, you could see this by calculating the partition function. Let's see, 1, 2. Now we have to add a source. So if we add a source to this equation, then we could take the derivatives with respect to the source, set the source equal to 0, and see that the propagator is in fact the same. Well, it's anti-symmetric, the propagator, compared to the bosonic case. So thank you. I hope you learned something today, and I will make more videos, and yeah, you'll learn more.